Extracting the sound is a good way to compare the noise before and after noise reduction. Hello, I'm Armin. In this tutorial, I'll explain how to use ANSYS Sound to investigate the radiated sound from a muffler and a straight tube at a distance of 1 meter after modeling them in Harmonic Acoustics. Before using ANSYS Sound, I'll show you the modeling process step by step, from creating the geometry to defining the microphone. So don't worry, and watch the tutorial until the end. Let's get started.
I want to create a muffler and a tube, then compare the transmission loss and the sound radiation 1 meter away from the muffler. To begin, I add Harmonic Acoustics. The first step is to create the geometry. I right-click the geometry cell and select New Space Claim Geometry. Now we are in the Space Claim module. I want to create the muffler on the XY plane, so I click Select New Sketch Plane, choose the Z direction, and then click Plan View to view the plane normally.
The inlet tube has a circular cross-section, so I select Circle from the Sketch tab. I click the origin as the center point, type 50 millimeters, and press Enter. Then I click End Sketch Editing to exit sketch mode.
This circle is the cross-section of the inlet tube, and now I need to extrude it. I select the circle, enter 100 millimeters, and press Enter. Note that the length of the inlet tube does not affect the sound transmission loss.
Next, I create the expansion chamber. I enter sketch mode again, select the cross-section of the tube, and click Plan View. Then I select Circle, choose the origin as the center point, type 150 millimeters, and press Enter. Before exiting sketch mode, the inlet tube should be hidden. This prevents the inlet cross-section from being imprinted on the new sketch. To show what happens if it is not hidden, I press Ctrl-Z, show the solid body again, and exit sketch mode. When I hide the solid, you can see that a hole has been created in the center of the cross-section.
To fix this, I press Escape, select the inner circle, and click Fill in the Design tab. Then I extrude the expansion chamber by selecting the face, choosing Pull, entering 300 millimeters, and pressing Enter. Finally, I press Escape. When I show the inlet tube again, we can see that the two bodies are separate. Now I create the outlet tube. I enter sketch mode, select the cross-section of the expansion chamber, and click Plan View. I select Circle again, choose the origin as the center point, type 50 millimeters, and press Enter. Then I click End Sketch Editing. As you can see, the outlet tube cross-section is imprinted on the expansion chamber, and there are now two circles. I select the outlet cross-section, enter 100 millimeters, and press Enter to extrude it. As you can see, there is only one solid in the structure tree because the geometry parts have been merged. This happened because no merge was not selected. This is the final geometry for the muffler model. Now we can close Space Claim. Air is available by default in Engineering Data. To check this, double-click Engineering Data. As you can see, air, structural steel, and water liquid are already available in the material library. Now close this window and double-click the model cell to open ANSYS Mechanical. The first step is to assign the correct material to the muffler. Expand Geometry, then click on the solid body. As you can see, the material is currently assigned as structural steel. Click the Material drop-down arrow and select Air. Now let's create a mesh for the muffler. Right-click Mesh and select Generate Mesh to see the default mesh size. The default element size is too coarse, so we need to define a smaller element size. I'm going to set the element size to 0.01 meters, or 1 centimeter. Press Enter, then right-click Mesh again and select Generate Mesh. This element size is suitable for this analysis. As a general rule, the element size should be no larger than 1/6 of the wavelength at the maximum frequency. Now, let's define the boundary conditions. We need one port at the inlet and another port at the outlet. Right-click Harmonic Acoustics, go to Insert, then Acoustic, and select Port. Select the inlet surface and click Apply. Then, for the geometry selection, select the muffler body and click Apply. Now we need to repeat the same process for the outlet. Right-click Harmonic Acoustics, go to Insert, then Acoustic, and select Port. Select the outlet surface and click Apply. Then select the muffler body as the geometry and click Apply. Now we have two ports, one for the inlet and one for the outlet.
Next, we need to define the boundary condition for these ports. Right-click Harmonic Acoustics, go to Insert, and select Port Induct. First, we need to select the port. Since port 1 is the inlet, choose port 1 from the drop-down menu. The wave type is set to planar wave, and the port attribute is set to inlet by default. Now we need to specify the amplitude. This value does not affect the sound transmission loss, so I'll set it to 1 Pascal and press Enter. However, this value can affect radiation results. Now let's define the outlet port.
Right-click Harmonic Acoustics, go to the Acoustic options, and select Port Induct.
Change the port attribute to outlet. As you can see, the pressure amplitude option disappears because this port is now defined as an outlet. For the port selection, choose port 2.
You can ignore the arrow direction here. The port selection is correct.
Everything looks good, and the inlet and outlet boundary conditions are now defined.
We also need to define a microphone for the exterior part of the muffler, so we have to add another boundary condition. Right-click Harmonic Acoustics, go to Acoustic, and select Far Field Radiation Surface. First, select the outlet of the muffler, because this is where the sound radiates from. Then click Apply. We also need to specify the acoustic body. Select the muffler body and click Apply. Now the muffler body is treated as a rigid wall, and the sound exits from the outlet. Next, we can set up the analysis. Click Analysis Settings to specify the frequency range. For example, I want to calculate the sound transmission loss from 10 Hz to 510 Hz. For the solution interval, I will use 50 steps, which gives a frequency step of 10 Hz. This is because 510 minus 10 divided by 50 equals 10. Everything looks good now, so we can solve the model. Right-click Harmonic Acoustics and select Solve. As you can see, there are no warnings for this simulation. Now we need to wait until the solution is complete. The solution is now complete. If we click Solution, we can see details such as the simulation time and the result file size. Now let's plot the sound transmission loss. Right-click Solution, go to Insert, then Acoustic, and select Transmission Loss. For this result, we need to select port 1 as the inlet and port 2 as the outlet. Then right-click the result and select Evaluate All Results. Here it is. This plot shows the sound transmission loss. The selected frequency interval is suitable for this example, but you can define any interval you need for your own analysis. Now, let's define a microphone in front of the muffler. Right-click Solution, go to Insert, then Acoustic, and select Far Field Sound Pressure Level Microphone. In the coordinate fields, we need to specify the microphone location. As you can see, the origin is located at the inlet of the muffler. For example, if I enter 1.5 meters in the X direction and press Enter, you can see the microphone moves along the X-axis. I'm going to change the X coordinate back to 0, then enter 1 meter in the Z direction and press Enter. This defines the microphone location. Now, let's view the sound pressure level at the microphone location. Right-click Far Field Microphone and select Retrieve this result. Here it is. This plot shows the sound pressure level at the microphone location. Now let's view the A-weighted sound pressure level. Right-click Solution, go to the Acoustic Results menu and select Far Field A-weighted SPL mic. Enter 1 meter in the Z direction and press Enter. Then right-click the result and select Evaluate All Results. Here it is. This plot shows the A-weighted sound pressure level, which represents the sound level as perceived by the human ear. If we increase the pressure amplitude, the sound pressure level will also increase. Also, as you can see, the SPL trend is opposite to the sound transmission loss. When the sound transmission loss increases, the sound pressure level decreases. Now let's extract the sound. Right-click Far Field Mic, then go to Export in the context menu. Here we have two options, Export to WAV file and Export to ANSYS Sound.
Let's start with the WAV file option, so I'll select Export to WAV file. The export window appears. In this case, it is better to select Harmonic Model because the inlet sound is a constant harmonic pressure of 1 Pascal, and it does not change with time. Then click OK.
I'm going to save the file on the desktop with the name Muffler. Now let's open the file and listen to the sound. This sound is not a real engine sound because the inlet pressure is not based on actual engine noise. However, we can still use it to compare the sound with and without the muffler installed.
Now, let's export it as an ANSYS sound file. Right-click the result, go to Export, and select Export to ANSYS Sound. Save it on the desktop, for example, with the name Muffler. After saving the file, ANSYS Sound will open automatically. There are 3 options for signal generation in ANSYS Sound. In this case, it is better to select Hybrid because this is the most suitable method for this type of result. Then click Generate. Here it is. This is the generated sound from the muffler at a distance of 1 meter. We can click Play to listen to the sound. The muffler label comes from the saved file name.
There are many options available for post-processing. For example, we can right-click the result and select options such as Calculate Spectrum, Calculate Time Frequency Representation. Here it is. This plot shows the spectrum of the sound. I'll zoom it to see it better. Remember that we only calculated the frequency range up to 510 Hz. Also, this sound is not a real engine sound. If the input sound were based on real engine data, then the generated sound and its spectrum would also be more realistic. There are many options available in the Calculation tab. Let's select RMS level versus time. ANSYS calculates the result over 10 seconds. I'll close this result and select another option. We can extract other results in the same way. However, note that we cannot extract all result types from this analysis. Now let's select Calculate TNR of Orders. As you can see, we encounter an error because this result is not available for a harmonic acoustics analysis. Next, let's select Envelope Computations to see the amplitude variation over time. The amplitude is always positive because the phase effect is excluded from this plot. This explanation of ANSYS Sound is enough for this tutorial, so I'll close the results and return to ANSYS Mechanical. Now, I want to compare the radiated sound without the muffler, so I'll close ANSYS Mechanical. Now, let's remove the muffler expansion chamber and replace it with only a straight tube. First, right-click Harmonic Acoustics and select Duplicate. This is the fastest way to create a copy of the existing setup. Double-click Geometry to open Space Claim. We are now in Space Claim, and I want to remove the expansion chamber. Click on the expansion chamber, then go to the Design tab and select Pull. Choose the Up To option, and then select the inlet or outlet tube. As you can see, the expansion chamber is removed, and now we have a straight pipe. Press Escape, then close Space Claim. Now we need to open the model again in ANSYS Mechanical. We are now back in the mechanical model. It is better to recheck the assigned material before solving. Expand the geometry node and select the solid body. As you can see, air is assigned to the tube. Now let's generate the mesh again. Right-click Mesh and select Generate Mesh, or click Update. The element size is similar to before, and it is suitable for this analysis. Next, we need to recheck the ports. This is port 1, and this is port 2. Everything is correct, so we only need to solve the model. Right-click Solution and select Solve. The solution is now complete. Now let's check the sound transmission loss. As you can see, the sound transmission loss is approximately 0 because there is no expansion chamber or absorptive material in the straight pipe. Now let's check the far-field SPL microphone result. Here it is. The SPL is higher than the SPL of the muffler with the expansion chamber. Now let's extract the SPL at the microphone location. Right-click Far-Field Microphone, go to Export, and select Export to ANSYS Sound. Change the file name to Tube, then click Save. Same as before, click Generate and select the hybrid method. This is the sound from the straight tube. We can also click Open and load the muffler sound in the same window for comparison. Here it is. This is the muffler sound, and this is the sound radiated from the straight tube. Let's compare them. As you can see, the sound radiated from the muffler is much lower than the sound radiated from the straight tube. You can perform all of the post-processing for both the muffler and the tube inside the same window. You can also find ANSYS Sound from the Start menu under the name Sound, Analysis and Specification. The tutorial ends here. If you found it helpful, please subscribe to my channel. Thank you for watching.